Hi everybody, thanks so much for coming. My name is Alan Cowen and I'm currently the Chief Scientist and CEO of a private lab and scientific consortium called Hume AI. I was previously a visiting faculty researcher at Google and a postdoc at UC Berkeley. About 6 years ago, I set out to develop new ways of modeling emotional behavior using computational methods. And I think those methods have really opened up exciting possibilities for understanding the role of emotion in our everyday lives. And so today I'm going to introduce you to those possibilities and attempt to give you a new perspective on emotional behavior and how we can train AI that understands it. So let me start by giving you my 2 cents on why computers might need to understand human emotion. And this is because I think it informs this problem of why we would want to understand emotions in video and how we would go about doing that. And so it goes back to David Hume's argument that reason is and only ought to be the slave of the passions. And the crux of that argument is that if you want to know what makes us tick, why we get out of bed in the morning, why we think about anything, why we do anything, you're eventually going to have to understand the emotions, why we feel things. In other words, emotions are the things that you're ultimately going to reference when your kid asks you why over and over, like why you're going to work, and why you need money, and why you need to feed your family. And eventually the answer is going to be something about what makes you feel happy and what makes you feel sad. And if AI was aligned with our goals, it would have to know what makes you happy and what makes you sad. What's the ultimate driver of your decision making so that it can be the ultimate driver of its decision making. What this means is that we can't build AI that really serves human emotions until we build AI that understands human emotions. And the core thing that machines need to understand is what's in the black box in our brains. They need to understand how the inner representations that mediate between the challenges and opportunities we encounter and our emotional behaviors that we use to respond to these challenges correspond to subjective experiences of emotion, right? This isn't an easy problem, obviously. What makes it hard is that our environments are extremely complex, and so are our emotional behaviors. We express emotion with at least 40 different facial muscles, lots of ways we can manipulate our voice, many ways we can move our bodies, and many ways that we can describe our feelings with language. So to deal with these complexities, as we all know, scientists have historically made simplifying assumptions, like the idea that we can draw simple one-to-one mappings between emotion antecedents like spiders and a few prototypical facial expressions like the so-called fear face. And everything comes down to this, or perhaps everything comes down to valence and arousal, or perhaps we can train people to measure facial muscle movements comprehensively by visual inspection with the facial action coding system. And those approaches have all been helpful in documenting a lot of the broad functions of emotion-related behavior, but they don't generalize well to real-life contexts and expressions or predict real-life behavior, and that's the challenge for affective computing. So we need to go back to the drawing board with modern tools that weren't available to the founders of emotion science and revisit some of those old questions. And in this talk, I'll focus on 3 core questions that I think are really the core questions we need to answer. And the first is, what are the emotional behaviors that we as scientists need to explain if we want to build methods for AI to understand emotion? What is the range of facial expressions and vocal expressions and language and so forth? And I'll talk about how we've recently been collecting new kinds of data and developing new taxonomies based on new data-driven theoretical approaches to emotion. And the second question is, what are the antecedents of these emotional behaviors? Where do they unfold in everyday life? And here I'll talk about my work at Google, where we built new ways to measure nuanced facial expressions at scale in millions of videos and understand the contexts in which they actually occurred across cultures. And then finally, I'll talk about new work that's enabling us to see how these behaviors actually map to people's reported subjective experiences of emotion, which is the kind of work that's needed to build AI that's aligned with our emotional needs. I'll start with the question of what are the emotional behaviors that people actually produce and that we as scientists need to account for. So for the last 5 years, I've been mapping people's experiences, expressions, and perceptions of emotion in the voice, and for the face, in prosody, speech prosody, in music, the experiences people have in response to music, and the experiences people have in response to art. And in each of these modalities, we've synthesized first decades of literature and gathered lots of data to try to understand the breadth of human emotional behavior. And this is a visualization of our results for vocal bursts. So we gathered 2,032 vocal bursts, which are laughs, sighs, screams, sighs, grunts, from 56 actors. And we got thousands of participants to judge these expressions in a lot of different ways. And long story short, we found that people reliably perceive at least 24 distinct dimensions of emotion in different vocal expressions, which is obviously a much wider variety of emotions than traditional theories have considered. And we can think of this as a lower bound because it's still only a sample of expressions. And we learned that the emotions that people attribute to these expressions are more precisely represented in terms of specific kinds of concepts like anger and adoration than broad dimensions like valence, whether something is pleasant or unpleasant, and arousal. But these categories, despite being called discrete categories traditionally, are not actually discrete. They're bridged by continuous gradients, linking states like fear, surprise, awe, and realization, interest, and confusion. So now people have generally relied on just the 6 basic emotions, or valence and arousal, to represent emotion. So it's critical to go back and ask what these models actually capture. How much of the variance is captured by these ways of conceptualizing emotional behavior? And so now we can use variance partitioning to find out precisely, predicting judgments of the basic 6 from the full state space of emotional behaviors people distinguish, and vice versa, seeing how much the basic 6 predict. And when we do that, we find that the basic 6 captures only about 30% of the systematic variance in what people take away from emotional expressions. This is true for facial expression, as you can see here, true for vocal expression, the taxonomy that I just showed, and emotions reliably reported in response to different videos, and we see this in just about every other modality as well, speech prosody, music, etc. And valence and arousal consistently capture less variance in each case than the 6 basics, about 29% or so. And more recently, we've revisited the facial action coding system because nobody has ever really tested the degree to which the facial action coding system actually captures the muscle movements that drive people's perceptions of emotional expression. And I get that that's what FACS is supposed to do. It's supposed to comprehensively capture all facial muscle movements, but it's never been validated in this way. And so we got thousands of facial expressions annotated by 2 of the best FACS coders I know, and we did variance partitioning. And the FACS codes were highly reliable, with a correlation of more than 0.84 across 53 different codes, but only captured about 1/3 of what facial muscle movements conveyed to perceivers. And that's because humans are natural-born experts, probably, at reading facial expressions, right? Not at trying to infer the underlying facial muscle movements that correspond to facial expressions, which is what FACS is built for. And the techniques that FACS coders learn and rely on are relatively coarse and heuristic driven, right? They're dependent on a lot of extraneous things, like having the right lighting so that you can see certain folds in the skin. And by the way, I didn't set out to knock FACS. Just about every researcher I've published is in love with FACS, and I like FACS. I think it's a good objective way to be able to link certain kinds of facial muscle movements to expressions and perceptions of expressions. So it's not like this is a tribal claim that I'm making. I'm just trying to move people forward to see that FACS is not the end-all be-all. It's not going to capture everything. It captured less than 1/3, in fact. And so we confirmed, again, that the basic 6, core affect, and other appraisal dimensions like safety and novelty also capture only a small fraction of what people perceive in facial expressions, which we can more comprehensively map with things like free response. And it turns out that if we have a big enough taxonomy of emotion categories, it captures about 92% of the variance in free response, which of course captures all of pretty much the basic 6, core affect, 13 appraisals. Doesn't quite capture authenticity, so that seems to be a slightly independent thing. And there's things about FACS that it doesn't capture naturally, because FACS will make distinctions between this muscle over here versus on the symmetric side of the face on the other side, which perceptually doesn't necessarily have any meaning. And so if we're going to capture these expressions in a comprehensive and unbiased way, how do we do that? Well, I think the best way is through large-scale experiments in which we have some semblance of experimental control over the emotions that people experience and express in different cultural and demographic groups around the world. And so that's what I've set out to do more recently with my new private lab and scientific consortium, Hume AI. And we've been gathering facial expressions, vocal bursts, speech prosody, multimodal data that's large scale, balanced across all of the dimensions of emotion that we've discovered and more, and captures emotional expressions from around the world, starting with the US, China, India, Venezuela, and Ethiopia, and includes self-report ratings so that we can avoid perceptual biases and confounds by gauging participants' own representations and beliefs about the meanings of their expressions. And I'll show you what some of that data looks like. So I'll start with our data set of vocal bursts. We started by replicating our previous work that I showed you on vocal bursts at a much larger scale, and then we recruited thousands of people around the world to produce their own versions of each expression and report what they themselves think they're expressing. Here are some examples. So we have over 200,000 of these labeled with people's own self-report judgments. We've done something very similar for facial expression. Again, replicating our work, much larger scale, gathering people's own facial expressions around the world and reporting what they themselves think those facial expressions mean. So what we can do with that incredibly rich data is train machine learning models that recognize facial expressions with a lot more nuance than anything that's been available before. For example, this is the first model that we've trained. It's trained on about 190,000 facial expressions, and it's able to recognize the expressions that people associate with emotions as subtle as love, or guilt, or contempt, or shame, and awe, versus, say, negative surprise. You can see that these incredibly nuanced differences will make a huge difference when it comes to training empathic technology that understands whether something is desirable like awe or undesirable like negative surprise, even though they're very structurally similar. So we can train models that take video or audio or images and automatically differentiate the more nuanced expressions, facial muscle movements, vocal modulations, to which people tend to attribute lots of distinct meanings, which brings me to my next topic. The question of what are the antecedents of emotional behavior? When do they occur in everyday life? And here I'll talk a bit more about my previous work at Google, where we built algorithms to detect some of the nuanced facial expressions at scale and examine the contexts in which these facial expressions occurred around the world. So based on my earlier work on the taxonomy of facial expression, Gautam Prasad, my colleague, trained a model that was able to distinguish a variety of nuanced facial expressions, and it worked pretty well for 16 different expressions. And as you all know, we have plenty of algorithms that we can use to classify contexts that occur in video, which means that if we look at enough naturalistic videos, we can now actually compare the contexts that co-occur with many different kinds of facial expression for the first time. And the fact that most of the world now has internet access and millions of people post videos online means we can look directly at the correlations between expressions and many different contexts all over the world. And so we gathered 3 million videos from 144 countries that were uploaded publicly online from mobile phones and that had people in them, and we analyzed whether the contexts in which different facial expressions occurred in the videos were similar or different across cultures. And so to answer that question, we first divided the world up into 12 cultural regions based on language, ethnic makeup, and to ensure a balanced distribution of videos around the world, and each region had over 100,000 videos. So I'll show you the results we get from these regions, but bear in mind that when we look at individual countries that have sufficient data, we actually get similar results. And in each region, we correlated across videos how often each expression was found on average within the video, and the contexts captured in the video. For example, here, each of these squares represents one of our 12 regions, and the color of the square represents the correlation between occurrences of the triumph expression, this one here, and the context team sport. And what you can see is that the correlation is positive in every region, based on the fact that the colors are red, and meaning that the triumph expression occurs during team sports all around the world. And this echoes classic findings in psychology by Jess Tracy and others that, for example, Olympic athletes from different cultures, even if they're blind, show triumph expressions when they win. But we can now look at this in the context of a much broader space of context expression associations found in millions of normal people around the world. So for example, we can see how specific this association is, and to do that we can compare these correlations across different contexts and different dimensions of facial expression. And what you can see is that the correlation between team sports and the triumph expression is pretty darn specific, but you can also see a broader story unfold, with correlations between a number of other expressions and a number of other contexts that are just as remarkably consistent across cultures. And that's easier to see when we normalize within each context because the contexts occur at such different rates. So drawing your attention to that red diagonal here in the middle of the plot, the diagonal is nearly uniformly red because the correlations are so consistent across cultures. And you can see that across every culture, expressions of awe occur in videos with fireworks, toys, and puppies, concentration with martial arts and school, contentment with weddings and birthdays, desire with candy, doubt with protests and police, pain with weight training, and triumph not just with team sports, but also with dance and rock concerts and individual sports. And we've repeated this analysis for over 600 different contexts, and now we can finally ask how well facial expressions are preserved across cultures by correlating these context expression correlations pairwise among the 12 different regions. And we found a minimum correlation of 0.7, which means that about 70% of the variance in actual context expression associations caught on camera is preserved around the world. And the next big question is whether these facial expressions really tell us what people are feeling. We know from our previous study of thousands of emotionally evocative short videos scraped from the internet that the range of emotions people reliably report spans at least 27 dimensions, which is a much broader space than past studies have considered. So to answer the question of whether these correspond to different facial expressions, we've now had thousands of participants in many different countries record themselves while watching each video and then report on their experiences. And so far we've collected 240,000 reactions to over 2,000 videos in over 10 countries on 5 continents. Here's one example.
Oh, yeah.
So you can get the sense of how rich these are. So by analyzing these with machine learning, we can not only compare emotional expression to experience, but we can model moment-by-moment variations in expression and really capture the deeper nuances and dynamic properties of these signals. So we decided to run models to find out how nuanced these expressions really are. And it turns out that at the aggregate level, we can predict a wide range of reported experiences from facial expression. So on the left, you can see the experiences that participants reported after watching each video. And on the right, you can see that the average predicted experience from expression along 12 dimensions that we were able to differentiate, which included things like surprise, fear, sadness, empathic pain, disgust. And so expressions do actually convey aspects of emotional experience. We can find almost all of these expressions in both Western and, for example, Japanese study populations. So these are some of the highest loading examples on each dimension. I'll leave this up for a second. But there are big differences between cultures in the average intensity with which these different emotions are expressed. So Westerners, for example, including in the US and the UK and most Western countries, express amusement, disgust, joy, and romance with at least 60% more intensity of facial movement on average than people in Japan, for example. Now, it's extremely important to take these differences into account, because if you don't adjust for the differences in expression intensity across cultures, it looks like only 16% of the variance in the expression to experience mapping is preserved across cultures. But if you take intensity differences into account by normalizing the measurements, an overwhelming 81% of the variance in the mapping from experience to expression is preserved across cultures. And this is for the US versus Japan, which were the most distinct cultures that we could find. So again, if you take these differences into account, you can often predict emotional experience from expression within and across cultures pretty accurately. So here are a few examples from top to bottom. You can see the stimuli, the reactions, one in a Western country, one in Japan, and self-reported emotions. And finally, the emotions predicted from the expressive reactions by our model in the West and in Japan. So overall, we've begun to put together a taxonomy of emotional behaviors, learn how those behaviors map to different kinds of antecedents of emotion, and how they correspond to emotional experiences. But this taxonomy is still provisional, and like, for example, the periodic table of elements, which I think is one kind of analogy for what the taxonomy of emotion could be for emotion science, I believe it's just a necessary step toward a more cumulative science of emotion and toward developing the ingredients of empathic artificial intelligence. The next step is to understand the causal functions of different emotional behaviors and how these building blocks of our interactions and relationships come together normally, and how they can vary across individuals and when those variations lead to dysfunction. And the next step to addressing these questions in a cumulative way and making consensual progress in the field is to have rich data that we can use to build computational models. So what we've been doing is collecting the data that's needed to support a cumulative science of emotion, a unification of emotion science and affective computing, baseline models that allow us to measure emotional behavior at scale, and we've been providing these tools to scientists to advance our understanding of human emotion, and to industry teams that are looking to develop empathic technology that adheres to our ethical guidelines that we're developing. And beyond myself, we now have 4 AI researchers, a psychology researcher, and a number of scientific advisors involved. And we're open to more partners and collaborators in academia and industry who can use our data to develop beneficial empathic AI. We also have funding for more AI researchers if you or anyone you know would be interested in joining this effort. To find out more, check out our website, Hume.ai. You can also find links to all of my papers that I've discussed on my personal website, alancowen.com. Thank you so much for listening.